Okay, time to get going. So here's where we were last time. We were looking at this example of how to compute a triple integral in cylindrical coordinates. And we talked through this whole slicing thing. And remember, the big idea is underneath all of what we're talking about here, yes, we are doing a change of variables. Yes, there is a pullback. Yes, there is a pullback domain. The whole idea is we don't need to draw it, because everything we need to know about it we can see right here in the existing picture. And all you have to do to get that benefit is just make the proper interpretation of what appropriate kinds of slices look like. So in particular, theta slices look like that and kind of rotate around the z-axis. That's just how it turns out. So anyway, we did this example last time. Remember, the last bit of which was that we had selected an r and a theta. Right? We talked about our theta slices, talked about r slices of a theta slice. This is what we're sort of left with, and lower bound is obviously r. The interesting one is the upper bound, which, thanks to our decent picture that we're working with, we can see right away is on the sphere. The sphere has this equation in cylindrical coordinates. Now, of course, you do have to convert from, you may have initially written it down in rectangular coordinates, right? So you got to convert that to cylindrical coordinates to get what you need. And then reminding ourselves that we are looking for a z bound. In this equation, we solve for z. And that is that upper bound. Okay, so that's where we ended last time. Now we're going to do the same question again. This time we're just going to slice in the other order. I say other. There are two what I'm going to call reasonable choices for orders of how to slice up this thing. And so the other is where I put the dr d theta on the inside. Now remember, always together, always in this order, right? But we're going to put the dr d theta inside of the dz instead of, as previously, outside of the dz. So, okay, with that in mind, let's think about what do z slices look like. All right, well, there's a z slice, right? Constant value of z. And that z slice of our ball is just a disk, right? Okay, first and last. Well, the first is obviously down here where z is obviously 0. The last slice, now here's where you got to think about geometry a little bit. That last slice is up there, the z coordinate of which, if you think about it, is in fact a radius. This is a radius of the sphere that we're looking at. And so that z coordinate, being a radius, is the radius. Okay. All righty. So with that set, we're going to fix a value of z, in other words. We're going to confine our attention to this z slice. Now let's think about the theta bounds. Now this is kind of an easy one, looking at the theta bounds, because look, theta slices are just kind of like this, and I'm going to say they pretty clearly just go all the way around. And remember, this is one that you want to have locked and loaded and ready to go. All the way around means theta goes from 0 to 2 pi. Right? So again, these bounds, nice and convenient in this case. And then, as usual, we fix now a slice of our slice. We're going to confine our attention now to just that little segment again. And on that slice, now we ask the next question, which is, all right, let's think about r. What's the starting and ending values of r? And again, one of these is easy. The lower bound, where do we start our r slices? Well, it's right there. It's on the z-axis. That's where r is 0. And so what's the value of r where r is 0? Well, it's 0, right? Nice little freebie. And then let's see, the last one. Here's where you got to be careful. That upper bound for r, it's at that point, which again I notice is on the sphere. And here's where it's dangerous. I claim just a little bit of danger here. A lot of people can be like, oh, same point on the same surface, same equation. Well, then it's going to be the same bound. And a lot of people think incorrectly that it'll just be square root of a squared minus r squared again. and it's not. Right? The difference being here, we are no longer looking for z. We're not going to solve for z because we're not looking for a z bound. In this example that we're doing right now down here, we are looking for an r bound. So we solve this equation for r as a function of theta and z. And that then becomes our r upper bound. Does everybody follow that? That makes sense? All right. Okay, so it's a lot like doing integrals in polar coordinates. It's just kind of three-dimensional, and the slices look different, appropriate to just the nature of cylindrical coordinates, right? But it's still, you slice appropriate to the coordinate system and think about the range of values and all of that kind of stuff. So it's just equivalent but adapted appropriately. And while we're here, I'm going to go ahead and remind you, don't forget to write down your stretching factor as you write down your differentials. It's so easy to forget otherwise. If again, you don't have to, but you're rolling the dice. You're gambling every time you don't do this, that you're going to forget to come back and insert it in here. And again, it's unavoidably worth a lot of points, and why take the chance is my take. Okay. All right. So cylindrical coordinates, a lot like polar coordinates. Different geometry, but same basic structure of strategy. Same with spherical coordinates. Again, we just have to think about what do the slices look like, and let me go ahead and zoom, yeah. So what do these slices look like? And I will confess, these slices are weirder looking, right? I don't have any knives at home that can do this, right? How is this a slice? That'd be a pretty weird cut to make. Right? And this I could probably do, but again, still pretty strange and geometrically challenging to think, oh my gosh, I've got to think about how does some solid intersect with these spheres. It is very sort of intimidating at first. Okay, here's the really good news. Again, there is a best choice for how to do your slicing. And I'm going to, to be fair, there are a few counterexamples. Gosh, they're rare. Don't worry about them. It's not going to affect us, right? The best choice is going to be to put your differentials in this order. I urge you not to even entertain other options. It's just going to throw a wrench into your works of your pattern of how to think through the geometry of the slicing process, pointlessly to no benefit in any case I've ever seen arise organically. Right? So just always do it in this order. And the good news there is that when you do it in that order, well, let's notice we're going to start with theta slices. Awesome. Theta slices are familiar and not that bad geometrically, nice and flat. Okay, now here's where I start to get a little scared. I got to do phi slices now. Phi slices look like this. Yikes. But I only have to do phi slices of my theta slice. I've got to think just about how that intersects, for example, with one of these green theta slices, and that intersection is actually really simple. It's just a line like that, sort of angled off of the z-axis, but again, flat and straight, right? And the fact that the actual phi slice is weirder looking, it doesn't affect us because we only care about what it looks like in the theta slice. And then, again, a little bit scary. Uh-oh, what are we going to do about this? Well, remember, we are already confined to a phi slice of our theta slice. That's all we really care about. So all of the ugliness and confusing and geometrically challenging, artistically challenging, how do I draw that, etc., no problem. All we're actually going to be doing is looking on one of these, seeing the range of values on one of these slices of, where does rho start? Well, that's going to be some value of rho. And then where does rho end? That's going to be some other value of rho. So in fact, in practice, if you follow this rule and if you keep your differentials in exactly this order, the slicing process is actually pretty straightforward, geometrically and artistically. Okay. All right, so that's good news. Now, a couple of bits of advice. Again, these are all familiar. Always, please, I urge you, write down your stretching factor with your differentials. Otherwise, you're going to forget a certain fraction of the time, and again, you're just leaving points on the table, right? The mere writing down of the stretching factor, correctly, of course, points, right? Get those points on the board, get them done, and don't trust yourself to remember it. Okay, I won't give that speech again. Again, how do you find a given bound? Well, you identify the corresponding points, identify what surfaces they're on, identify what are the equations of those surfaces, and then solve for what you want. Okay, alrighty, let's get into the geometry of some examples. Our domain here is going to be this ball, not centered at the origin, annoyingly. Right, so this is offset in the upward, so the center's on the z-axis. So it's kind of sitting, if you will. It's like it's sitting down on the xy plane, touching at the origin. All right, so if this were a domain for a triple integral, how would I slice that up? What would be my range of values for my spherical variables? All right. Okay, theta slices. Like so. All the way around. Right, again, you got to have a picture to make sense out of this. Make sure you have a decent picture. So I see from the picture, it goes all the way around. So theta is 0 to 2 pi. Again, nice, easy one. Before we go on to the phi slices, here's a trick that I like to pull. You don't have to do the following. I find it helpful. There's this ever-present challenge of visualizing the geometry, and it's hard because it's three-dimensional and we're using two-dimensional paper, and it's a toughie. I like to take my representation of my theta slice and just redraw it where I'm looking straight on at it. I find that a little bit easier to work with, right? I mean, in some sense, like if you think about it, let's think about that line right there, that direction. In reality, that's actually horizontal. Right? On the page, it looks like it's tilted downward. So we're dealing with an illusion. Right? It's not that you can't make sense out of it, it's that it's just a little bit harder. So you don't have to, but I encourage. Redraw it. And let's see here, let's remind ourselves what our slice looks like. Our actual theta slice of our solid is a half disk. So I'm going to draw a half disk like this. There's our theta slice. And now let's think about what phi slices look like. Again, I don't need to worry about the actual phi slices. I only care about how the phi slices intersect my theta slice. And as we've previously discussed, that's just going to be rays coming out of the origin. Is everybody on board? Is everybody with me? Okay, so we just got to think about first and last. Well, the first one is like this, which is straight up, which is where phi equals 0. So phi starts at 0. And then, well, let's see here. For my last one, I mean, my slices kind of go like this, and they proceed along, and they keep going and going and go, and they get smaller and smaller the more closer I get to horizontal. And then finally, my last one, beyond which it's total swing and a miss, is when it's horizontal, and that's pi over 2. Everybody see the geometry on that? It's just purely geometric argument here. Let me give you a warning about I'm going to call it a landmine. There is a very common mistake that students make, I get it. You know, I understand how this slip-up can happen, but again, it's our job to make sure we don't make slip-ups, so we got to, anticipate. I like to show you where the landmines are, as it were. Very common for students to think about phi imagining that it emanates from the center of whatever they happen to be looking at. Right? So we're looking at a disk that's kind of sitting up here above the origin. And so sometimes people just reimagine phi like that, and then in their mind, their phi slices look like this, and they're going to then get the wrong answer because they're going to think that it goes all the way down to pi, and it doesn't, right? That's just not what phi slices look like, right? So you got to make sure to keep yourself honest, right? Make sure to adhere strictly to where do phi slices start, right? They always start at the origin, right? And that's how you're going to come up with this correct answer. All right, yeah?
Would it ever be better to move the bounds of the interval so then we'd start at the center there?
Yeah, sure. So that is a reasonable approach that you could take to this problem. And again, my purpose here isn't to get the answer. My purpose is to give an example of a slicing process. But yeah, you're totally right. It would be depending on the integrand, depending on other details, to do a change of variables where your pullback domain is centered at the origin, and then life becomes much simpler. Yes, absolutely. Yeah. Okay, but again, as a slicing exercise, here we have our theta and phi bounds. And now let's think about our rho bounds. And so we think about for example, phi slice of our theta slice, like so. We think about first and last values of rho. Well, we clearly start at the origin where rho is clearly 0. That's, again, sometimes you get freebies. The non-trivial one, the last value of rho is going to be at that point. That point's on this curve. Wait a minute. Where's that curve? There wasn't a curve in the original question, right? How do I know what curve is? Where was my algebraic foot in the door on that curve? And here's where you have to remind yourself that curve, that is that curve, where did that come from in the first place? Well, this was a redraw of that, and this little piece of curve is actually part of the sphere, right? So you can write down now the equation of the sphere, and that's the equation that's going to give you your upper bound in question. Okay, now one little hoop you got to jump through. You do have to convert that equation into spherical coordinates. Again, we're going to be solving for a spherical variable. We're going to need to solve for rho. So whatever that rectangular equation is, okay, well, it's a start, but I can't work with that. Convert to spherical coordinates. Then you can solve for rho, and that will give you your rho bound. Everybody good? Kind of like that last example that we did in polar coordinates. You got to actually do the conversion process. And again, how to convert these equations we talked about back in chapter 1. Okay. Now I'm going to make a claim. Again, I can't justify because I have these notes written in advance, but I claim that I wrote this all down all at once. Rho squared sine phi d rho d phi d theta all together. Don't forget that stretching factor. I can't emphasize it enough. That's points. Right? Get those points. Lock them up. Okay, a couple of bits of advice about drawing as pertains to these kinds of examples. There's no getting around the fact that it's essential. You've got to give an argument to justify your conclusion, right? Where did these bounds come from? In other words, a purely algebraic argument is, at best, brutally opaque and inconvenient and fraught. Right? You don't want to try to make an actually legitimate algebraic argument justifying these bounds. So the picture is basically the only way to do it. If you're going to make a geometric argument, you got to give me the details of that geometric argument, and a picture is unbeatably the best way to do that. So make sure that you're good with drawing pictures, and if you're not, you need to figure out how to get good at drawing pictures. A couple of bits of advice: Don't make a little teeny tiny little postage stamp size little picture. A lot of people focus a little too much on saving space, right? Make these teeny tiny little pictures, and there's a lot going on, and you're going to need to, if the picture's too small, you're just going to have a lot of problems, right? So make a nice big picture. I think a case could be made that these pictures that I've drawn are kind of bare minimum size. A case could be made, maybe they could have been bigger. But in this case, we kind of got away with it. These pictures didn't get too cluttered. Let's see here. Don't expect that you're going to just look at the description of the question and then just kind of see what the domain looks like in your mind, and that you will just then draw it, and then presto, you'll have this beautiful picture. Nobody to speak of can do that, right? I suppose maybe some real, highly experienced right-brained, left-brained people who are just amazing in both maybe might be able to do that, but it's not a good realistic target, right? So I certainly don't. I always draw a first picture with the understanding and expectation it's going to be bad, right? But then I learn a little something from it. I get a little bit more of an intuition of what this thing looks like. That allows my second picture to be better, which allows me more intuition for what the solid looks like that I'm trying to describe, which makes my third picture even better, possibly even good enough, right? And then repeat, just, as many times as necessary, right? But again, don't try to just nail it on your first shot. Do keep in mind on exams, you have scratch paper, right? So I encourage you to make your initial drawings on the scratch paper and learn all the lessons you need to. Lastly, and again, this is just, I think this is really important. So don't try to just rely on your intuition for drawing. Maybe you have excellent intuition, and that's great and all, but there are little points of technique to know. Some of it's chops, just the actual mechanics of how to make a good job, do a good job with drawing with a pen, right? And some of it is points of strategy of what should you draw to represent what are you trying to represent. And so it's what I'm going to call technique and points of skill, right? So benefit from the experience of others, right? And now I've got these videos on my YouTube channel and the Miscellaneous Topics playlist. I think it's everything I know about mathematical drawing. I get by, right? And I think it's probably good enough. But there's probably more out there to be learned. I sort of assume there is. Feel free to research further than that. But at a minimum, I think what I have on my recordings would be a good thing for everyone to know. And then furthermore, it's more than just knowledge. It is actually skill, technique, chops. You got to be actually good at it, and that unavoidably takes practice, right? So I encourage you to spend some time focused on just how to make good drawings. Okay. All right. Moving along. Here's another one. Another ball. Again, offset. This time offset in a different direction. And it's tempting to say, it's an offset sphere that goes through the origin. We just did an offset sphere that goes through the origin. How's it going to be that different? And fundamentally, spherical coordinates is not really all that symmetric, right? Spherical coordinates is the z-axis is special, right? So this is not going to be the same. And we just got to think through the geometry here again. Now we'll start with theta slicing. Again, always differentials in the same order. So starting d theta, here's what a theta slice looks like. Does it go all the way around? No, it really doesn't. Right? In fact, I think it's a pretty easy pitch that if I were to look at a slice kind of going back into the negative y part of space, there's nothing back there, right? So I claim that looking at these actual slices, the very first one is going to be where theta is equal to 0, and then the very last one is going to be where theta is pi. And again, this is purely a geometric argument. The picture communicates that to some extent. You might not consider that to be really sufficient. A perfectly reasonable thing to do would be to get, you get some Play-Doh or something, make yourself a ball, right? And then take a knife, be careful please, and just start making cuts, right? And just doing like that. And what you'll notice is arranged like so, sort of sideways are the first and last cuts. So, if you don't have Play-Doh, you can get an orange, right? I assume they have fruit at the dining hall, right? So get yourself an orange and think about slicing that up, and then you get to eat an orange. It's win-win. So anyway, 3D models can help. Let's see here. Okay, so as usual, we fix a value. So we're going to look at this theta slice. Again, I like to redraw just to make it a little bit easier geometrically, so I don't have to deal with the illusion of it being sort of turned sideways otherwise. And now let's think about our phi slices. And of course, phi slices emanate out of the origin, sort of like so, which on our picture over here would be kind of like this. Right? And now let's think about first and last. And I suggest that the first slice, again, we've got non-trivial slices like so as phi gets smaller and smaller, and the very first one is there where phi is 0. Right, and then our phi slices continue, again coming out of the origin. And then our very last one is going to be like so, where phi is pi. Everybody see that geometry? And again, just appeal to what the picture tells us. All right. Okay, so as usual, now we fix phi and theta, thinking about our phi slice here of our theta slice, as usual. And we got to think about first and last. Well, the first value of rho is going to come from, that point. That is the first part of our phi slice of our theta slice, and that's the origin. That's where rho is obviously 0. Right? Our last point is going to be that point right there, which I can see is on this circle, which of course comes from the sphere. And the sphere, again, there's a little bit of work to be done, and make sure that you can do this, right? But you can write down the rectangular equation of the sphere, which you can then convert into spherical coordinates, in which you can then solve for rho, and I claim that you get that. So fill in those blanks, make sure you can do that, and your upper bound then for rho is that because of solving for rho. Everybody good? Okay, so again, reminder while we're here, easy to forget, worth the reminders. Don't forget your stretching factor, and again, write this all down all at once just as a trick to avoid possibly forgetting. Okay. All right. So that's most of what I wanted to say about spherical coordinates. I am going to really quickly point to this one last example. This is just a kind of a little artistic trick. The math is fine on this example. I'm going to leave all the math to y'all. You can just read this example. It's a lot like the ones that came before it. But it is a little hard to draw, and there is a clever little artistic idea that will help you go through the slicing process. So what this thing looks like, we have here this ball. Which is like this. And now let's think about what this says right here. It looks like a ball until you notice that is a greater than or equal, not a less than or equal. So that means I'm looking for points that are outside, not inside, outside of the unit ball. So I'm going to draw that kind of like this. So I want the points that are inside the green and outside the red. And now again, geometric appeal, you got to think about how that looks, and I claim that what this looks like is, now it's going to be hard to draw, and I'm going to do a poor job of it, and then I'm going to show you how to deal with this. Something vaguely kind of like this, but again, kind of like an example that we saw when we were doing triple integrals, rectangular triple integrals. This has got there's kind of a cavity that's, it's like I have a melon baller, right? And I have a melon ball, and then I scooped a divot out of the bottom of my melon ball with the same melon baller. And so there's actually melon right there. And further behind the melon, there is a cavity. Behind the cavity, there's more melon. How am I going to draw that? Right? It's a tough draw. And then we have to face the further artistic difficulty of, I've got to figure out how to draw the slices of the thing. I can't even draw itself. And so that's a little frustrating. So here's the big idea. First, just a little bit of language. I'm going to refer to this as being, I'm going to call that an intersection. It's not the intersection of these two balls, but it is the intersection of this top ball with the exterior of the bottom ball. So I'm going to call it an intersection. It's kind of an intersection of sorts, just to make the language a little bit easier to talk about. When I'm trying to draw cross sections of an intersection, this is the big artistic trick. Cross sections of an intersection are just intersections of the relevant individual cross sections. And the good news about this is that these cross sections, the cross sections of the balls themselves, super easy to draw. Nothing to it. Right? So for example, if I wanted to take a theta cross section, a theta slice of, let's see here, let's start with this one. What does a theta slice of that ball look like? Well, yeah, nothing to it. It's a half a disc. That's easy. Just to have a clearer picture, I'm going to draw it over here. It's this. Like that. No sweat at all. Nothing to it. It's a slice of a ball. Easy. Okay. Now, what about if I were to take a cross section of this lower ball? Well, again, it's a ball. It's still centered on the z-axis, and the slice is still going to be, something vaguely like that. And again, just to make it a little bit prettier, I'm going to come over here, do like that, and then referring again back to what I claim is the big trick here. We're trying to draw cross sections that we can't even visualize of an intersection that we're having a tough time drawing on its own. But we're going to do it by looking at the individual cross sections. There they are. Nothing to it. Individual cross sections. And all we got to do is look and see how they intersect. And it's so much easier since we've already taken the cross sections. If I want to know, what does it look like, the thing that is inside the blue but outside the purple? Okay, well, yeah, nothing to it. It's, let's see here, color choices. It's this thing here, like that. So I think that's a really nice little artistic little bit of trickery. I hope you'll find that convenient. And then the slicing process, again, same as usual. This is a good example to think through. Do notice, last time I'll mention it, I I've included the stretching factor along with my differentials. Got to write those down at the same time. And just go through the usual slicing process. And then I will also point out while we're here, another lucky break. We end up with another one of these equilateral triangles. All right, it's sweet when that happens. Geometry helps us to find some of the relevant values that I'm interested in here without having to do any trig. Very convenient. Okay. All right, so that's it for triple integrals. Okay, moving along to symmetry. This is some of the most underappreciated material in the course, in my opinion. I have worked my way up to some material that we're going to make a lot of use of in this class. I think you'll find what I'm about to show you will be useful in a lot of instances in your future. I think of this as being one of the top. Whoa, let me not overstate it. Definitely top 5, maybe top 3 most useful integration techniques that I'm aware of. All right, this is really, really cool, and a lot of books undersell it, and invoke it here and there, but never really explain why it works or what they're doing. And some books don't mention it at all. I don't get that at all. Anyway, here's the big idea. You've actually seen a symmetry theorem already previously in single variable calculus. You'll recall that there was a discussion, should have been anyway, of what it means for a function to be odd, what it means for a domain to be symmetric, and when you have a symmetric domain for an integral with an odd integrand, that integral is 0. Does that look familiar? Hope you all have seen this. Very often they'll present the symmetry of the domain as they'll have the integral go from like negative a to a, or something like that. The left bound is the negative of the right bound, and they say it in different ways. So let's talk about why this is true, and I think this is pretty satisfying why this is true. Here's the classic single variable, Calc 1 picture. Of course, it's a graph, right? So full disclaimers, graphs are very convenient and single variable, but a little over relied upon, in personal opinion. But if you're computing an integral of an odd function will look kind of like this, in the sense that the value there and the value there are opposites of each other, so it'll have this kind of a look, right? And the terms in the Riemann sum will be a height times a width and a height times a width, like that. Right? Now, we know from the oddness that f of negative p is the negative of f of p. That's just what it means to be an odd function. And then I make the observation that this blue term in the Riemann sum is that. This green term in the Riemann sum is this. And it says right here, right, what this equation says is that these are opposites of each other. They're opposites, and so in the summation, they cancel. Right, is that satisfying? Right, everybody's kind of seen some argument along these lines anyway before, something analogous to this. You might have heard it instead presented as, and again, single variable calculus instructors like to rely on this idea that an integral is an area. And again, that's one of the applications, and that's cute and all, but that's not fundamentally what an integral is. Okay, just look, had to get that behind me. But if you think of this as area, and this area is below the x-axis, we're going to think of this as negative area, right? They love that pitch. And again, there's a point of view. Anyway, negative area, positive area. The areas pretty clearly look like they cancel again, suitably interpreted, right? So this is what I've given you here is just a kind of an algebraic version of the same thing, just thinking of it as terms of the Riemann sum instead of areas. Okay. Now, for whatever it's worth, you can also prove this with a substitution. I'm not going to go through this algebra, but I think it is a good exercise, and I hope you'll take a look at this. It's no Riemann sums required at all. Just from the fact that you have a symmetric domain, you can make this substitution, and you can show by doing a change of variables through that substitution that this integral is its own negative, which means it's got to be 0. Clever little argument. Okay. Details for you to look at if you're interested. So you're not responsible. You don't have to, but I think it's a healthy exercise. Okay, so I just want to make the observation that you can do pretty much exactly the same thing in 2 dimensions. We just have to adapt these ideas appropriately. And the big idea is, instead of talking about an x value and its negative, we're going to talk about reflections over a line. And I appeal to your sense of, sort of the geometry of 1 dimension, that when you take a negative, you are in fact kind of reflecting. You're just reflecting over the origin. Here we're reflecting over a line. We're reflecting over a 1-dimensional thing because we're looking at 2-dimensional points. Okay? So this is a generalization, kind of a natural extension of that previous idea. And with the idea of a reflection, we can talk about symmetry. Symmetry just means that when you reflect, you get a minus sign. Just like with odd functions in Calc 1. Same basic idea. And we can still talk about what it means for a domain to be symmetric over a line. And just geometrically, symmetric means that if you flip it over the line, it remains the same thing. Right? It's like a Rorschach test kind of a thing. And this is how you write that down mathematically. And again, you don't need to sweat the details there. And with these ideas, you get the same theorem. Morally the same theorem. It's super powerful. It comes from the same place as that single variable theorem. And here it is. If you have an odd integrand that you're integrating over a symmetric domain, that integral is 0. Totally awesome. When this theorem applies, oh my God, we didn't have to slice anything. Right? I didn't have to find any bounds. I didn't have to do any single variable, inside integral, outside integral, wait a minute, which is the variable, which is a constant. No, just, a couple of clever observations, boom, done. Right? Pretty awesome. I'm a huge fan of this theorem. Now let's be clear on the catch. Several catches, kind of, depending on how you look at it. You do need for both of these conditions to hold. One of the biggest mistakes I see students make is they see a symmetric domain and they're like, okay, integral 0. Not true. Right? It's just not good enough for the domain to be symmetric. Function's got to be odd. You've got to be able to get cancellation, right, in the same way. The other is, and this one's subtle. A lot of students mess this up. Catastrophic results. But it's got to be the same line for both of these symmetries. Got to be the same line. Right? So do be careful about that. Make sure you're using the same line for both of these symmetry arguments. Now let's see why this is true. And again, you can make a substitution argument, aka change of variables. The reflection is the change of variables function. Again, you're not responsible for looking through this, but it is very, very analogous to the substitution argument we made for the Calc 1 integrals. So take a look if you like. Totally analogous, but again, you're not responsible. You don't have to. And And here's the Riemann sum argument that I think is much more satisfying, and that is, look, if you have a line of symmetry, and if your domain is symmetric, right, as I have it drawn here, that domain's symmetric. If you flip this domain over that purple line, right, it looks exactly the same. If we're willing to be generous to my art attempts there, right? Symmetric domain. So here's the idea then. Any little piece of the domain has a corresponding term in the Riemann sum. This little piece of the domain, its reflection, there is a corresponding term in the Riemann sum. And wait a second, but this is an odd function. Being an odd function, I know that this is true. Right? An odd function is a function where if you reflect the input, you negate the output. Right? Just like in single variable. And then we get this same punchline that these two terms, right, there's a green term in that summation and there's a blue term in that summation. And because of this minus sign in the summation, they cancel. But I think geometrically, this is much more sort of like geometrically satisfying. A little bit more visual. You can kind of see the cancellation happening, whereas in some sense here the cancellation is a little bit of hocus pocus hidden in the algebra and the cleverness. And here it's right here looking at you. Okay. All right. So let's see how this works in practice. Let's get one done. And here we go. This is what we want to compute. We got a domain bounded by a couple of curves, and we want to. Oh my gosh! Look at that nasty integrand. Oh wow! But this is gonna stink, right? Just visualize how you're gonna look at this. We got e to the power of a quadratic. Oh, there's a times something. Oh gosh, this is gonna be integration by parts for sure. Man, that's gonna. I don't like the looks of this. Right? By the way, it's even worse than this. You got to think about how you're going to slice this thing up, and keep in mind whatever your inside bounds are, which is going to have a quartic in it somewhere, is going to get into your integrand. So it's way worse than what we're looking at here. Right? This is a nightmare of an integral. Oh, okay, so let's try to find a different way to do this for sure. I don't have to come head on at it. First observation to make: if I were to draw this domain, let's draw x squared minus x to the fourth, and this is a Calc 1 thing, right? Y'all remember how to plot curves, and I claim that it looks approximately like this. Oh gosh, I'm doing my best to be artistically competent. Something vaguely kind of like that. This curve right here, y equals -1, is going to be something like that. We are interested in this region that's bounded by those curves. It's something like this, and I'm going to kind of point to the picture and say, well, it's pretty clearly symmetric. Right, specifically, it's symmetric over the y-axis. If you take this domain and flip it over the y-axis, nothing happens. It remains the same exact shape. Everybody buy that? Okay, now I am relying on that assertion. I'm relying on the idea that this curve is symmetric. How do I argue that curve is symmetric? Well, if you do the reflection, so the reflection over that purple line, this reflection just takes whatever your x coordinate is and negates that x coordinate. The y coordinate stays the same. X just turns into the negative of what it had been. So that's what our reflection looks like. And if you just do that to the green curve, you get the exact same equation. So that's the argument for how I know that this green curve is symmetrical. Is everybody okay with that? Okay, so we've got a symmetric domain, sweet, over the y-axis. Let's see here. Now I am going to claim that my integrand is odd. Reminder, odd means that when you put the reflection into the function, you get a minus sign out of the function. Right? So let's check and see what happens. Let's actually do it. I'm going to take this reflection, I'm going to plug it in to this function. Oh gosh, let's see, I'll use orange. I'm going to plug it in to that function. Now, that's kind of what you get, and you can see the reflection happening here, because where there had been an x, there is now a minus x. Right? That's the evidence of me having plugged the reflection into that function, and then just crank out the algebra, and just really you just gotta do the algebra, follow the laws of algebra, do what it says, and the punchline is that yes, indeed, when you reflect the input, you negate the output, just as required. So we have an odd function integrated over a symmetric domain. Boom, integral 0 by symmetry. We didn't have to deal with the antiderivatives of this monster, or certainly not the much worse monster that it would have been had we done the bounds and the inside out, etc. So we avoided massive amounts of effort with this nice little trick. And I'm out of time, so sorry to go a little bit over. Y'all have a good weekend. See you on Monday. Don't forget about attendance if you came in after I did the thing.